Alrighty. Alright, let's see. Yeah, microphone's working. Hopefully people are there. Let's see. So first thing I see. Wait. Alright. First, someone type in the exams channel and let me know that I'm actually live and you can hear me. Everyone ready? Or there's no one here. Uh-oh. Alright, at least one person. Alright, so let's see. First thing we shall do. Oh, it might be mono. Yeah, the audio is definitely mono. I don't think I have an easy way to fix that, sorry. I guess we'll have to deal with it. Yeah, I didn't install that software. Oops. Alright, so sorry it's mono. We'll have to deal with it. So, let us start with, I guess we'll start with this question, the file systems question. It's one I heard. Yeah, your left ear is going to hear it. All right, so let's start with this question. Assume file system block size 4096. So always write powers of 2. So that, and 4 byte pointers, that's to the 2. And then 128 byte inodes to the 7. All right, inodes have 12 direct pointers, 1 indirect pointer, 1 double, and 1 triple. So calculate the total bytes needed for 100 files, each 100 bytes in size. Include the size of the inodes in your calculation. You may skip the file calculation if you don't have a calculator. All right. Was it MIDI setup? Sorry, the dogs are making it difficult too. Input, mute through. All right, no easy way for me to fix it right now. All right, so it says calculate the total number of bytes needed for 100 files, each 100 bytes in size, include the size of the inodes in your calculation. So each file, as we hopefully know from lab 6, it needs a inode. So 100 files, that's 100 inodes. So this is, okay, from inodes. Plus, well, you know, we can only get a block at a time. So even if it's 100 bytes, we need 100 blocks. So 100 times 4096. Okay, sorry, 1 second. The dogs are going crazy. All right, sorry about that. Off to a good start. Whoops. Oh, nope. That did not fix it. So, so this is from the blocks. So that should be, if we can skip the final calculation, doesn't really matter. So whatever this number ends up being. It says how many bytes are lost due to internal fragmentation for the files described. So our block size is 4096, and we're actually using only 100 bytes to store the file. So for each file, we are losing, what is that? 3,996 bytes lost per file. So times 100 files, that is whatever this number is. Large number. And then let's see. So what is the maximum file size supported by the triple indirect block? Well, first we have to keep track of the number of pointers we can store on a block, right? Same idea as like with virtual memory. So that is block size. So 2 to the 12 divided by 2 to the 7 is 2 to the 5. So that's per block, or sorry, whoops, sorry, it shouldn't be the inode size. That is the pointer size, my bad. So 2 to the 10 inodes per block, and if we have a triple indirect block, well, that's 2 to the 10, all to the power of 3. So we have 3 different levels, so that's 3 to the 30 different blocks we can point at. So that's how many blocks max for triple. Oops, triple. So then the total size of the file is the total number of blocks we can point to times the size of a block, which is 2 to the 42, which is what, like 4 terabytes. All right, next one. Why do we not just use a single triple indirect block instead of having direct blocks? Main reason, it's slow. So having direct blocks is a lot quicker, right? If our file only consumed 1 block, I would need, like virtual memory for a process, you need at minimum 3 page tables. I'd need at minimum 1 level for each block. So it would be wasteful. It would also be quite slow. Okay, a whole bunch of other questions not related to this. We use a direct and indirect pointer space. Oh, yes, okay, that's a different question. All right, 26. How would you support a maximum file size at least 100 times more than it's currently supported without changing that size or the number of pointers? You may change how they are used. So -1 direct, +1 quad indirect. Oh. So you just swap one, you could just swap one of the direct ones for quad indirect. And then we can suddenly address a whole bunch more things. All right. Okay. Dogs, please be quiet. All right. What's other things we need to go into? Look to the question if you have a time, not sure. Okay, that is a page table question. Let's see if there's any other full questions. Oh, so don't have that one available. An example about in pipes and out pipes, not sure what you're talking about. We went over a pipe question. Nested RAID levels, sure. So, let's just go to a blank page. Let's talk about nested RAID. Nested RAID. So, basically the whole idea between nested RAID levels is, well, I can combine like RAID 1 plus 0. And what that means is across the top, I can have it behave like a RAID 0, which is just striped, right? So I can actually, each one of the, I don't know, children, I think, if you want to think of it that way. Each one of the children here gets, in this case, if RAID 0 has 3 different disks, or 3 different things it's pointing at, or 3 things that look like disks, then the data is going to be split a third on the first, third on the second, third on the third. So the idea behind RAID 0 is like, well, instead of RAID 0 going to a physical disk, I'll have it go to a RAID 1 array. So each of these individual stripes goes to a different RAID 1 array. So it looks like this. And then that RAID 1, well, each of those RAID 1, that's the actual disk. So unlike RAID 0, where everything's striped, and if I lose one, I lose all my data, well, now every stripe has a exact copy of itself, so I have to lose both sides of the stripe in order to lose data. And as a bonus, if I get really lucky, I can lose one copy of each stripe without losing data, and then I'm good. Maximum file size of at least 100 times means like, so here we go back. I guess the audio delay is bad. So at least more than 100 times. So we've calculated our max file size before, right? So we had 2 to the 42 max before. And 100 times means, well, our file size we want to support now should be bigger than 100 times 2 to the 42, whatever that number is. So new max should be much, much, much greater than that. And, well, with a quad indirect, even with just a single quad indirect, right, it's 2 to the 10 all to the power of 4, which is 2 to the 40. Times the block size, so that means we could support up to a 2 to the 53. So 2 to the 53 is at least 100 times greater than 2 to the 47. In fact, it's 1,024 times greater. Okay, so it did that. You might have to refer to the answer. How we answer this kind of question. Okay, so. Okay, unlike other years, everyone seems to be very concerned about one of the CS111 ones. How do you answer that? Okay, so let's go to this. All right, so we should be able to see this. And yes, the stream is only in your ear. And quad indirect would not mean we have more pointers. It means we're using one of the pointers now for a quad indirect block instead of a direct block or something. Or you could say instead use the triple. Yeah. So we want this one here. One sec, let me see if I can fix an easy way. Click edit, advanced. Edit. Advanced audio properties, sync, monitoring off. Boom. Okay, is that better? Oh, that looks a lot better. Okay, so there, I found the button. I found the button. The microphone should be in both ears now. Please say it's in both ears. Okay, the stream delay is also terrible too. I think I did not. Okay, good. All right, so it's stereo. All right, so you can see this screen now. So let's start going over this file system question, because this exam, so this is CS111 fall. So here's the disk question. Wait, this has answers. What's the question for this one? Why this question? So someone else says, how would we answer this question? Kind confused about the wording for A. All right. So using your knowledge of file systems to explain the difference between ln and cp in terms of inodes and blocks. Assume you have a file called my-file.txt that contains 2,290 bytes. The block size of the file system is 4,096 bytes, so it fits on a single block. As a hint, I ran the ln and cp commands. You'll find the output of ls after the command shown. So ln a file, so that's a hard link. We should know what it does. And then here, the question assumed you didn't know what copy does, so that's what it was trying to ask you. So we cp'd myfile.txt to cp-file, and then we did ls. So we can see that ln-file is a hard link to my file, so they have the exact same inode number, and cp has the exact same size. Knowing we've probably used this command before, the contents would be the exact same, but the hint here is that the inode, hi mouse, is that the inode itself is different. So the first one, explain what happens on the file system when you run the ln command. Start your explanation at the new directory entry for ln file. So when you do an ln command, or when you add anything, a new name to the directory, right, that goes to the directory inode first. So it has to figure out, okay, what's my current directory, figure out what inode that's on. Now you know, doing lab 6, the contents of a directory are basically just name inode pairs, so it would add a new entry for that called ln-file, and it would be assigned to the same inode as my-file, so in this case inode 101. On the inode itself, you increment that link count, so the number of hard links to it, that gets incremented, and I even let that one slide for the question, and the blocks are unchanged because, well, the inode points to the blocks, I'm pointing to the same inode. So does that, hopefully that answers that. Okay, I think that got answered. All right, this question next, the next one. And then we can do a threads question. So this one, virtual machines. All right, you have a single server that hosts a web server, database, and streams video. Over time, as your server gets used more, you find that it's now overloaded. You decide to buy another server. You could move one of the 3 applications to the new server and hope it's balanced. Given that you've taken this course, you think using virtual machines would be a good idea. Assume containers do not exist. How would you organize your applications into virtual machines? Explain how many virtual machines you would make and what would go on them. Well, easiest thing to do is just, assuming we are using containers, just because I wanted to constrain the answers a little bit, you just make a virtual machine for each application. So one for a web server, one for a database, one for streaming video. And assuming they're all doing the same thing, there's not that much traffic, well then I can just run each of them on the same computer, no problem. I can share all the resources, it doesn't really matter. Then if one gets overloaded and I buy a new machine, I can actually look at the usage of the virtual machines, know which one is used the most, and move that one over to the new server. And you could migrate that virtual machine a lot easier than it would be to like reinstall a whole application and all of that. Next one, what would the benefits of using a virtual machine in the event one of the 2 servers is now overloaded? Well, just move it, like I said before, just move it to a new server. You could even do a live migration. That means I can physically move it to a different server without shutting it down or anything like that. So no option whatsoever. Neat. All right, so that's what that says. All right, so we want to do, all right, next one I said is the threads question on the latest one. Yeah, I think that's, anyone with audio problems, I think that's your issue. All right. So here is our threads question. So this again is 2024 winter ECE343. All right, so this is the threads question. So it says, consider the provided code which handles multiple socket connections. You don't need to know how sockets work. Again, like I told you don't need to know the connect, bind, the listen, blah, blah, blah. Sockets are IPC though, so they do read and write system calls, all the same. And for the question, why do we need to create virtual machines for each application? Because, well, that's the easiest way to divide things. Okay, so, sorry, back to this question. So it says each independent connection runs in a new thread. The key functions include the next index. So that is key function number 1. For server selection and run task for running the task. We want this code to cycle through all servers in a fair and orderly manner. We also want to ensure each server executes the run task function no more than once at any given time, while allowing for simultaneously run task executions on different server. Spoiler alert, this came up because you know how you submit you push your code and then it runs on some servers. Well, those servers are sitting beside me right now, and this is pretty much exactly the code that's used to figure out what one of the 4 servers your code should run on. So here, let's read the code. So you're given a struct, the server has a name, you're given that the number of servers is 4. You have some global variables, you have a global server index, and you have a struct server, so 1 for each server. Then you have a next index where you create a local variable. Let's point here. So you create a local variable called index, which is a copy of server index, which is a global, so that's going to be a memory read. And then you increment server index. Oh no, well, just looking at that, we know incrementing a global variable, if 2 actions can happen concurrently, then we might have a data race. So I'm already on red alert for this. Then it says if server index is greater than num servers. Oh, so now I'm reading it after that. Ooh, that might also be bad. Then reset the server index back to 0. All right, then in the run function, it says we're guaranteed each thread gets a unique task ID. So it's given from that argument. So the argument, let's just backtrack into the main function. This PFD comes from here. It gets malloced. Doesn't appear we ever free it, so that's not good. So that's just the file descriptor. Okay, the dogs are going crazy again. Sorry, 1 second. All right, sorry, back again. All right, so where were we? We were at our run function. So we get a task ID, guaranteed that each thread gets a unique task ID. Then it calls this wait index. Oh no, that happens in different threads. So we probably have a data race with that server index then. Then it says, prints off a line, start a task ID with the name, then run the task. It says run task does not access any global data. So that's probably good. That means we don't have any data races with that. And then it just has a printf with the end task. So it says an example output would look like start task 1 on server 0, Eventually they all get ended, so I might not know what order they are in, but this should come after this. This should come after this, and so on and so forth. So within a thread, they should be ordered. And as soon as a thread or a server is done, it can pick up a new task, might be able to end immediately, no problem. So it says this input would not be valid. We start a task on server 1, server 0, and before it's done executing, we start another task. That means we're executing 2 tasks at the same time on the same server. That's not good. All right. First question says, examine the next index function in the provided code for potential data races. Is there a data race when updating the server index variable? Yes. So the answer is of course yes, because here we have 2 concurrent accesses. That this is all running with, let's say, we created one for each. Well, we don't even know how many threads are running. So you could have multiple threads all running this run function. That calls the next index function. So we can have concurrent accesses to the server index variable. So first thing it says is propose a solution to fix it. And then if no, don't have to worry about it. Reference specific line numbers or annotate the total correctly. You not have to write initialization code for new variables if they require a value to initialize, to state what it is. So that is to cover the case of, hey, if we need a center for, just tell me what the initial value is. I don't care about the syntax. But here, easiest thing to do is just create a mutex, call it m, who cares, equals init, don't have to remember. And then easiest thing to do here is just to have a lock of the mutex before we read anything, and then before we return the index, which is a local, we do an unlock. So now we turn that whole thing into a critical section. Now, only one thread can execute at a time. We don't have a data race, we're all good. So hopefully everyone's okay with that. And yeah, we have 2 dogs and there's currently 3 dogs in the house. Yeah, so we're fostering one right now who is loud. Okay, so that was question 5. Next question says, analyze if it's possible for a server to be executing 2 run task calls simultaneously in the given implementation. If this scenario is possible, suggest modifications to ensure that the run task only runs once per server at a time. If not, explain why the current setup prevents multiple concurrent run task execution on the same server. Reference specific line numbers or annotate directly in the code for clarity. You may add fields to the server start on line 5. You do not have to write initialization codes if they require a value to initialize them. Just state what it is. So currently, they could be running the same task at the same time, right? Looking at this code, I could just call get index, and then before the other task is done, so let's say next index now returns 0, then I start a task on server 0, and then before it starts, I have a whole bunch of other threads, call it 1, 2, 3, and then they all run their own tasks, but now it resets back to 0 because it rolls over. And now I don't know what the order is between anything. I could run another task on server 0 So two concurrent things could happen at the same time. Easiest way to fix this is, well, if I want to make sure only one task runs at a single time, then I can use a mutex again, or I could use a center-for. Doesn't really matter in this case. So for fun, I guess to be different than the solution, and I guess to illustrate a different initial value, I could use the center-for each server. So I'll just call it, wow, that was a weird thing. So I'll just create a sem underscore t, call it sem, and then I'll figure out what its initial value is. So I'll just say init, and then with some value. So for that, the easiest thing to do, again, is to just place the weight. So here, I could place the sem weight, and that would be for this specific server's semaphore. So it would be servers index dot sem, and then it's the address of that, but who really cares? And then after it's done, then, well, it could run again. So this would just do the same thing, sem post of this whenever it's done. And then, well, my initial value would be 1, because I want one task to happen at any given time. If I wanted two tasks to happen, maybe simultaneously, I could change that initial value here to 2 if I wanted. And the way I like to think about it is the initial value is how many threads can actually call this weight value without any other ones posting at all. So if the initial value is 1, only one thread can get by, right? Because it atomically decrements, it would take the 1, change it to 0. Now, if any other thread comes in without a post, current value is 0. It's going to block there until another thread posts it up. So one of them can actually successfully increment it. The initial value is 2. Then I can have 2 threads call wait and pass by it successfully, because 2 would be decremented to 1, 1 would be decremented to 0, then other ones would wait. Then question, just to confirm, we could also unlock before line 17. So if you put the unlock here, then you might have issues. So if you put the unlock there before the condition, let's go over that because that's a fun one. So say I put the unlock call there. Usually for data races, if something very bad and unexpected happens, that wouldn't happen with a single thread, then that would probably be a data race, that would probably be bad. So right here, right now, I can never see like an invalid, I never return an invalid server index, right? So if I had it like this, what might happen is, let's say I have thread 1 and thread 2, both calling this function, and the server index, let's say for fun, server index is currently at 3. Right? So if server index is currently at 3 and we have 2 concurrent calls for this, okay, well, we have a lock, that's good. So this will create a value called index, and then it will be equal to 3, and then it will increment the global variable up to 4, and then unlock. And now thread 2 can immediately run. Now it gets an index equal to 4, which is bad because index 4 does not exist. And now it doesn't matter what happens. So both of them would try to update that the server index equal to 0 eventually. Don't know what order, but they're both going to eventually write 0 to it. But it doesn't matter. We're kind of screwed at that point anyways, because thread 2 is going to return an index of 4. And that is going to be an array index out of bounds. We'll have a whole bunch of stuff, blah, 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 blah. Then there's a question, shouldn't we do something like sem init? Sem 00, so that's like the actual, whoops. That's like the actual thing for it. I guess in this one, oh yeah. So yeah, in the given functions, I did not give you sem init because I don't care about the arguments or anything like that. Just the only thing that really is important is the initial value. So as long as you tell me what it is, I don't really care about the syntax. And you should know it has an initial value. If I just gave you the signature of sem init, it wouldn't say what that value is for or anything. It would just say it's one of them. You know it needs some value. This video will be uploaded. Will scheduling be on the final? It's technically fair game, but probably won't be. I mean, you did scheduling on the midterm, right? So, all right. Anything else to go over? Are we expecting the same big question category like the two other finals? More or less. Yeah. Let's see. What can I say without giving away too much? Yeah, more or less the same. One might be different. All right. Can we go over the clock algorithm? Try and do clock, FIFO, LRU if it's possible. All testable second algorithm. Clock should be, oh, there's one clock. What was the clock question everyone thought was the solution was wrong? Which question is that? I think it was 2023 final. Was it this one? Can't tell if this is, well, let's do this one. So, someone asking how to quickly do the clock algorithm question so that need to draw it every step. You pretty much need to draw it, but we can do some shortcuts. Let's see how fast we can do it. So, oh, it is, someone said it is 2021 fall. Okay, let's see if we can pull it up. So here, VM. This one's wrong, someone was saying. Oops. It's this one, right? No, that one's correct. The second last one is wrong. The optimal for one. Okay, I'm not sure which one's wrong. Anyway, to check if we've done it correctly, just double check your work. Here, we can do a quick example because we can do them relatively fast. All right, so this one is the 2023. So this is 2020. Oh, this is 2024. I'm pretty sure. Yeah, this is 2024 winter. Whoops. Last step where you're inserting one is wrong. No, it's not wrong. Okay. Let's just do this one quick just to make sure. So this is 2024 winter ECE343. All right, so it says use the clock algorithm for page replacement. Recall that on a page hit, you'll set the reference bit to 1. It even tells you for each page access to all pages in memory. After the access in the boxes below, state the number of page salts for accesses. So I'll do this in black because, well, that's what you'll have on the exam. You'll probably have one color. So I'll just circle all of the page misses. We all know that the misses are going to happen first, and the clock's going to be calculated or populated like this. So I'll have 5-1, or sorry, 4-1 is first. I always like starting pointing up at the top. So I have 4-1 first. Then I go to 1-1. Then I go to 3-1. Then I go to 5-1. So this is what my clock looks like. Oh, there's only 3 memory spots. Oh yeah, there's only 3. Whoops, my bad. Okay, sorry. Rewinding. Woot. All right, so the first 3 are easy. So let's rewind time. Assume I read the question correctly. All right, so there's my beautiful clock. So, first thing, page 5 gets accessed. Oh, it's not in memory. If we do the shortcut, then we just change all the reference bits to 0, right? So we just change all the reference bits to 0, and then 5 is going to replace 4. So 5 is going to go in. We're going to set it here, so it would be 5-1. And then we would take the hand, oops, and advance it. Now, when we access element 1, well, that's a page hit. Again, we want our hits to be really fast. We're not going to move the hand or anything like that. We're just going to set the reference bit back to a 1. And we're going to draw it as if nothing happened. Then same, okay, now we access page 4. That is not in memory, so we're going to have to kick something else. So then here, well, we're currently pointing at page 1. Its reference bit is 1, so we just change it to a 0. Then advance the hand, looking for a new victim. Then we're currently pointing at page 3. Its reference bit is 0, so that gets kicked out. So we are kicking out page 3 for page 4. So write out our page fault there, and we can insert it. So now we kicked out page 3. We put in page 4, and its reference bit is now 1. And we'd also advance the hand as part of the last step, so we don't immediately try to kick out page 4 since we just put it in. Wouldn't make sense to try and kick it out again, right? So then we access page 1 again. Oh, it is now already in memory, so we update its reference bit from a 0 back to a 1. So that would be another page hit. Access page 5, still page hit, still good. So nothing changes. Now we access page 2. Oh no, we can do our shortcut. Oh, cool, there's an email saying the location may be incorrect. Excuse me? How do you guys get that email and I don't? So I assume if I don't get that email, that's fine. Anyways, back to the question. So the shortcut, if all the reference bits are 0, instead of the clock spinning all the way around, I know I can just immediately set all the reference bits to 0 instead of 1, because I know it's just going to swing all the way around. So now I'm currently pointing at page 5. I would replace that for page 2. So I would put that in here. And yeah, it's getting a bit messy, but this is what happens on the exam when you can't actually erase stuff. And then advance the hand, so now I'm pointing at page 0 again. Now I access page 4. Again, it's in memory. I want the update to be really fast, so I just change the reference bit to a 1. So still looks like that. Now I access page 5. I have to kick out something. Oh, I'm already looking at my victim page 1. So I kick that out for page 5. Boom, like that. So that is clock algorithm, nice and fast. Next one part says optimal. So optimal, same idea for the first 3 accesses. Going to be real boring because I have to populate memory. And then next is 5. So with optimal, that means I look into the future. So I look into the future and use the page that's not used in the longest. So next page is 1, can't replace that one. Next page is 4, can't replace that one. Oh, so the last one left is 3. So I would replace that for page 5. So it would look like that. Now access page 1, well, look at me, I was a genius. So I went to the future and I made sure that my next accesses were all hits. And now page 2, well, I have to look into the future. I don't want to replace page 4. I don't want to replace page 5. So optimal thing to do is just replace page 1. So it would look like that. And then for sanity checking, all these questions want the number of page faults. In my diagram, it's just the number of circled things. So for the clock algorithm at the top, that's 7 page faults. And then for the optimal algorithm, that was just simply 5 page faults. And good sanity check that you should always do. If your optimal has more page faults than the clock algorithm, then you did it wrong. Okay, so double check. Let's see if I got, so I didn't get an email from the university or anything like that. I have to check. I can't check Acorn because I don't have Acorn. Faculty final exam schedule. I have to check Power BI. Ooh. So our exam, unfortunately, still tomorrow, still at 2 p.m. Still looks exactly the same. Oh, student range updated on November 29th. So, yeah. So, surname, whoops. Yeah, so just check that you're actually in the right room. Uh-oh, I lost it. No, you don't need to remember the spelling of Belladie's anomaly. Just know that there's an anomaly and it's silly. Yeah, the Zeds get their own room. Yeah, Zeds are in Wahlberg. It's a very small room, but I guess we take what rooms we can get. Yeah, at least we're not in a church and community center this time on Spadina, so that's an upgrade. Oh, okay, we still were doing the threads question. Because people are confused about what one. Oops. So we were doing the threads question. Okay, so I think that was it. Okay, so some people are confused with the last part here. So for the thread question, it says, assume that the task runs arbitrary code. I guess you may have not heard of that. Arbitrary code is just me just taking random code from the internet and running it. After taking this course, should any of you trust random code that you have not written, given all the silly things we have done? Probably shouldn't just run random shell scripts. You know, we figured out how to create fork bombs and all that fun stuff. So arbitrary code is just code someone else gives you. Not a good idea to run that. So this assume that the task runs arbitrary code. In this example, I have one process. I have a whole bunch of threads. Each threads are running a task. And if a thread is directly running that task, then it could do anything. So if one of those functions that the task is running does something like, I don't know, segfault or exit the process, then the process is dead, all your threads are dead, and then nothing's going to get scheduled anymore. In fact, that whole web server is now dead. So you just brought down that whole server that was accepting connections and everything because there's only one process, ran someone else's code, it segfaulted, it just called exit, who knows what the hell it did, and now not going to run. A better approach would be at least running it in a different process. So if it crashes, then that's fine. Your code still works. You could actually, you could wait on that process. If it crashes, then you can see that it has a non-zero exit code. You can be like, oh, okay, it crashed, whatever. Better solution. Above that, if you want more isolation, hey, like your lab runner actually does, is it just runs it in a container, because your code could literally be anything, including things that can time out, as some of you have learned. So for this question 7, can the answer just be for loop and a while loop, as this also ensures order? No, because the run function is the only thing you're allowed to modify. If you have every process and then you call wait on it for each server, then yeah, you could do that. But question 6 didn't assume you were running in processes. Yeah. All right. Wait. What else do we got? All right. Let's see. What did I miss that we still need to go over? Question 7 did that one. Pretty sure I did question 19 on the other one. Can you explain hold and wait versus circular wait? Why does circular wait imply hold and wait, or is it hold and wait only really for lost wake up? So circular wait does not imply hold and wait. I think you're thinking of the deadlock conditions. So in order to have a deadlock, you have to have all 4 conditions. The only 2 we can do anything about is circular wait and hold and wait. So circular wait means there's a cycle of dependencies of holding a lock and acquiring a lock. And also hold and wait means I have to hold a lock while trying to acquire another one. Both of these conditions have to be true at the same time in order to deadlock. If I break just one of them, then I do not have a deadlock. So they both have to hold. Doesn't really have anything to do with lost wake-ups. Can we do some short answer questions? 2021 summer. All right, so is the summer the one? The summer must be the one without any solutions. All right, so VM summer. All right, so summer. Again, people have been asking about this one, which is kind of weird because this was like a very small class and also during COVID. So page replacement, oh wow, it came up even then too. So here we go. So page replacement, whatever. Page tables. All right, consider a system with a 39-bit virtual addresses, 44-bit physical addresses, 4096 byte pages, and the page table entry size is 4 bytes. This system is impossible in practice. What aspect of the system needs to change in order for it to be usable? Explain why your change makes it usable. All right, so we can do this. This is a good kind of short question. So let me prepare, move it. So let me just rewrite out everything again. So this is, let's go. All right, so this is a virtual memory question. So just with the facts of the matter, we have a 39-bit virtual address. We have a 44-bit physical address. Our page size is 4096 byte pages. Again, you know me, I like writing powers of 2, so that's 2 to the 12. And then it also says the page table entry size 4 byte PTE size, which is 2 to the 2. Says this system is impossible to use in practice. What aspect of the system needs to change for it to be usable? Explain how your change makes it usable. So, what hints do we have here? Well, you can start off by figuring out, we can figure out a few things we already know. So the virtual address, that 39 bits is divided up into the virtual page number, which might be further divided up into levels with the multi-level page number, and then an offset. And we can figure out how many bits are in each. So for this system, my page size is 12, or 2 to the 12. So I need 12 bits to figure out which byte on a page I'm trying to access. And then by just doing the subtraction, there are 27 bits for the VPN. Similarly, for the physical address, it's made up of a physical page number and an offset. The offset is still going to be 12 bits, like before. And in this scenario, we have 44 minus 12 for the number of bits from the PTN, and that is 32 bits. Ruh-roh, I'm already seeing a problem here. So 4 bytes, that is also 32 bits. So in that scenario, we know a page table entry holds a PPN plus at least a valid bit. Although it'd be pretty useless if we just had a valid bit, we wouldn't have any protection or anything like that. Probably be at least a read, write, execute. And then, hey, if we have copy on write, we need at least another bit to keep track of whether or not a page is shared or not. But at minimum, at least a valid bit. So in this case, the PPN size must be at least, or the PTE size, sorry, the entry that has to hold the PPN and at least a valid bit needs to be at least 32 for the PPN plus at least 1 valid bit. Wow, that is the worst one I have ever written. So it needs to be at least 33 bits, and the page table entry size is only 32 bits. So it's impossible. So in order to change things, the change is change PTE to, likely it would just go to the next power of 2. So just increase the size of the page table entry. It needs to be at least 9 bits, or 8 bytes. All right, let's quickly go through the other ones. Threads. So here's a threads question. forks assume that blah 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 should be alright. Alright, so there's this one. Locks concern the following code. I have a read-write lock. I have a count equal to 0. Then I wrote a function called increment, and then I lock the read-write lock for reading, where I load the value of count into a local variable x, and then I do ++ x, so I increment a local variable, and then I write out the result to a count. And that says, assume the read-write lock gets initialized properly. Recall that the read-write lock locks for readers only, and the write lock locks for a single writer. The unlock call unlocks both types of locks properly. So, first question says, does this code have a data race? If not, explain why. If so, show an incorrect outcome using only 2 threads. So, the answer to this is, there is still a data race. Oh, whoops, you can't see the exam. So, the answer to this question, this locks question, is there is still a data race, because this is essentially what ++ to a global variable does anyways, right? Remember the Jimple code and everything like that? So it will do a load into a register and then increment its register and then update the global variable with the result of that register. So this still does the exact same thing, we just split it up. Here we're protecting the load and the store individually, doesn't matter at all. So I can still get 2 reads before a write. So still going to have a data race. Count could still be 1 after 2 threads call increment when the initial value is 0. So the answer is definitely still the data race. Then it says, without changing the lock to a mutex, keeping it as a read-write lock, explain what you'd have to do to prevent all data races. That is simple. I just use it as a write lock, so I get rid of all of this read lock nonsense, and at the beginning of the code, I lock it for writing, and then I do these 3 lines all in a row, and then I unlock it for writing, and then that's it. Then it basically acts as a mutex, no data races, all fine. And then other question, what if we only use 31 out of 32 bits for the virtual memory question? Can't do that because it tells you, like it tells you what the physical address is. So if I want to use only 31 bits for the PPN, I would have to decrease my physical address size, which goes against the design of the question. So you can't change the physical address size. I guess you could say that. I would probably give marks for that one. Wasn't the intended solution. But yeah, if you say, hey, I'll just support a 43-bit physical address, then sure. And no, the data race is not at the ++x part. The ++x is an update to a local variable. The data race part is that this read needs to happen, like this write has to happen after this read with nothing else coming in between them. So if something reads it, it needs to write it out before something else reads it. That's the problem here. Like it has to happen all at once. All right, next question. Locking. You want to write a program that has 1 thread and prints a status every 100 times process. You do this. So this is basically just did a mod and subtracted it. So it wasn't too bad. I'll skip that for now. Memory allocation. Assume you have a buddy allocator initially that has a 512 free block. All right, let's do this one. So we have a buddy allocator that initially has a single, what do I call this? Buddy. So we initially have a 512 byte free block. You cannot allocate more memory, so it's just controlling that 512 byte free block. So let's go here, tablet. So we are essentially managing 512 bytes, all in a big block. The first question says, essentially, we ask for like 200, we're mallocking 200 bytes of memory. What happens? How does the allocation occur with the buddy algorithm? State what's in the free list after the allocation. So we're going to round up, right? So 200 is not a power of 2. So step 1 is to round up to 256 bytes. Step 2 is, and remember, buddy allocator, we'd have a free list for each level. Initially it would be empty, so I'm just not writing what the free list is for each level. Next step would be to check the 256 byte free list. It's currently empty, so we're going to try the next power of 2, right? So then we're going to check the 256 byte free list, and way you know that's what we're managing. So we're going to take that 212 bytes, split it up into 2 buddies that are size 256. So we found. Next would be split, adding a free 256 byte block. So let's say this one is used and this one is free. All right, so part B, how many bytes are lost due to internal fragmentation after the first allocation? So that's simple. It is, we used a 256 block to store that 200 byte allocation. So it's just simply the size of that block minus the size the allocation actually wanted. So we get 56 bytes. All right, part C, it says, next we deallocate the 200 byte allocation. So let's just call this P, so we're like freeing P. Describe what happened, state what the free list looks like now. So what's going to happen is we're going to check buddy at 256 byte level. Oh, hey, you're free. Oops, so step 2 is merge buddies. Whoops, merge buddies. So we merge them back together. So now that 512 byte block is free again. And we can use all of that precious memory. So 3, add 256 byte block to free list. Merge buddies. And also we'd remove the 256 byte free. So that's what we look like now. So then part 4. Now we get 4 different 100 byte allocations. You don't have to describe the process, however, state the free list at the end of all 4 allocations. So part D is basically we get malloc 100 4 times. Sorry, microphone's in the way. So malloc, okay, I can write better than this. I know I can. So we'll malloc 100, and we will do that 4 times. All right, so each one of these internally are going to get rounded up to 128 bytes. So that means my 512 byte block will get broken up into 2 256 ones. And then that would get broken up into 128. So after the first allocation, this one would be used, this one would be free, and this one would be free. Now, to do all the other allocations, well, spoiler alert, first one, it's just going to use this free block. It's the exact size it wants. It'll be used. And then for the next one, it's going to split this 256 byte block into two 128s. First one's going to be used. Next one's going to be free. And we would remove this from the free list. And then for the last allocation, there's exactly that amount of memory left. That byte block's free, so they'd be used, one for each allocation. Then it says how many bytes are lost due to internal fragmentation after these four. So we are losing, 28 bytes per. So we have four allocations, so we could multiply those two numbers together, which is what, like 112. So that's how many bytes lost due to internal fragmentation. And it says describe an approach you could use to fit another 100 byte allocation with your original bytes. Assume you can use your approach to allocate all 500 byte allocations from scratch. So that whole idea there was, hey, I could just implement a slab, right? Implement slab on 512 bytes. So I could be like, hey, buddy, just give me all of your memory. So I get 512 bytes, and then I'll just have a slab. Slab is basically an array where everything fits together. So I could fit, in this case, I could fit 5 things on there, right? So if it was an array, I could have 5 different elements. They're all 100 bytes. They could all be packed right next to each other. Then this whole thing would consume 500 bytes. And assume, for a slab, we also need a bitmap. So we only have 5 things we need to keep track of. So, so this array is 500 bytes. In order for bitmap for this, we need 5 bits. Just round up, so we just need 1 byte. So we could have a bitmap here in 1 byte. So in total, our slab would take up 501 bytes if you really wanted to go into detail. But all I need for this question is just slab. All right. Other things. So is that okay for slab? All right, we want some short answers, so. Oops. All right, so this one has a bunch of short answers at the end. Question 7, advanced scheduling. What is priority inversion with respect to scheduling? How would you mitigate that? So priority inversion is a low priority or a high priority process is blocked waiting for a low priority process. So it, for that period of time, essentially becomes a low priority process because that high priority process cannot make any progress until the low priority process is done. So to mitigate that, we could do priority inheritance so that if a low priority task if a low priority task depends on a high priority task, then we can just temporarily inherit the priority of the high priority task. So while that dependency is being resolved, it can run as a high priority one, resolve it, and then it can go back to being a low priority after the high priority one is done waiting for it. All right. And then, back to the slab. what is the external fragmentation? If any, we wouldn't have any external fragmentation for the buddy allocator. But we just have internal fragmentation. And yeah, the buddy allocator, the 2048 game, it's essentially the same idea. We like powers of 2. All right, next one. Assume you have a NAND flash SSD with 4 kilobyte pages and 128 bytes per block. If a block is completely full, that means all of the pages have data. Explain how deleting a single page would work. You can assume that there's already a newly erased block that's writable. So remember with SSDs that you can only erase blocks at a time. So if I have a block full of data that's in use and I want to actually delete one of those, well, I can't just, or if I want to erase one of those, I can't just erase one of those pages. I have to actually move all of the other pages because I can only delete blocks at a time. So I would have to move the 127 pages that are still in use to that new block that's freshly writable, so I can just move them all there, and then I can erase that whole block that has 128 pages. So I'd have to move a whole bunch of pages is all I wanted for that. And then question 9, distributed systems, not in this course, so wouldn't worry about that. Virtual machines. Why do cloud providers heavily use virtual machines as opposed to giving customers access to bare metal hardware? To answer this question, name 2 benefits of virtual machines. Wow. So lots of benefits. One being that they can migrate virtual machines to different physical machines. If one goes down, needs to get rebooted, whatever, they had to buy more, things of that nature. Also, if you give them access to a bare metal machine, that means they can access hardware, they can access everything on your network, they can crash the machine, they could, try and update the BIOS, whatever. No one would be able to share that machine because if they have access to the memory, they're essentially running as the kernel. They could inject their own kernel code, whatever. You wouldn't be able to have one machine serve multiple customers at the same time. And yeah, so for the bitmap slab, I just showed that because that's extra detail in the lecture. I just assumed that it was small or whatever. And then wait, so if there's no writable block, you can't delete. Yeah, you'd have to erase something else. All right, any other questions? I think we covered them all. Oh yeah, file system question for 2023 fall. Okay. So request for a file system question. So where are we? This looks, oh, we did this. 2023 fall, it has check marks. So it is good. All right, other one. Oh, missed one. Also wondering, is deadlock defined as any thread stuck or all threads stuck? Here technically only half the threads are stuck. You could say a thread is deadlocked. So yeah, it depends. You can say a thread is deadlocked. That means the thread can't make progress. If you want to say all threads are stuck, then you can say a process is deadlocked. So those are 2 different ways you said. Generally for deadlock, if it's a thread or a process, either is fine, but you can technically divide them like that. What will we need to delete in that case? So if you can't delete anything, then your SSD is full. Otherwise, you're going to have to delete something and move around data. So that's part of the fun thing of managing an SSD. All right, so we did that question. All right, anything else we got? Any yeah, I mean, even if you just say deadlock and you just show one thing going, I don't care that much if you're that specific. It doesn't matter. But yeah, you can be specific if you want. Bit confused about the difference between external and internal fragmentation. Or would you have external fragmentation? Will apply if we do not define the size of a block. Yeah, so internal and external fragmentation just has to do, like, it's in relation to the blocks the memory allocator is using. So internal is within the blocks it's managing how much space is actually of that block is actually used for that user's allocation and how much of it's wasted. And external fragmentation is, hey, how many of my blocks are wasted, which depends on the size of the allocation. So for example, wait, where did I write that down? Yeah, so going back to this buddy allocator question, So, for example, when we had okay, did not mean to do that. That's the wrong course. So for example, for part D here, when we had all blocks used, we could say, hey, there's no external fragmentation. And what I'm talking about is this. So all the blocks were used for 128 byte allocations. But if instead, let's assume that, the last one I mallocked, well, actually I used all the memory, but let's assume that, I don't know, if I had something else where I had two of these were free for some reason, and I had someone ask for an allocation of, I don't know, 256 bytes. Well, there's no 256 block free because, I only have free 128 byte blocks, even though I could technically have enough space. So you would say for the buddy allocator that those two blocks would be external fragmentation for a large enough allocation. So it's basically just wasted space. External fragmentation is, hey, in total I have enough free memory, I just don't have enough of it contiguous to do this allocation. Internal fragmentation is within the block I gave you. I had too many levels. Quick question, how do you identify a 3-level virtual page number? How many bits does each index for each table entry get? Does it depend on how many entries are there per level? So with all multi-level page table question, the whole idea is we'll use a page to fit a page table. So you always need to calculate, hey, given a page size and a page table entry size, how many entries can I fit on a page? And then the number of index bits you need is just however many different indexes you need. So it'll be 2 to some number. That 2 to some number is how many bits you'll need to figure out which index you need to do. Also, other one. So that zombie question we went over in one of the lectures. So yeah, we definitely went over that in the lecture. For process 103, I would accept just saying always. That question has a whole bunch of different answers because I didn't specify a certain point of time. I probably should have said something like when process 100 terminates, what can its children be at that point? So can we do another thread and center for problem? Want to see the mindset of solving problems. For virtual memory, how does the kernel switch the virtual address space of a process? Like how to distinguish virtual address in process A versus process B? Is the root page table somehow stored in the process context? Yeah, so like the root page table is just stored in a register, right? And part of the process control block would save the registers. Even if it was a thread, it would save the registers that are and their current values. So it would save that as part of the context. And then when you restore, your root page table comes back because it's just used in that register. The next one, in the case, would the kernel be able to move one of the two 128 kilobyte blocks to the other one. Is the kernel allowed to move physical memory when it's needed, given the virtual mapping doesn't change? So the kernel is not going to move anything. The kernel only deals with pages at a time. Oh. Yeah, these aren't 128 kilobyte blocks. They're just bytes. But the kernel is not allowed to move it. This is any memory allocator, could be in the kernel, could be malloc. Even if they're technically beside each other, it wouldn't merge them because they're not actually buddies. So buddy allocator just simplifies things to make the algorithm a whole lot faster. Just to clarify, even though one thread is stuck, we consider a deadlock. Yeah, you could clarify and say that thread's deadlocked, but you can just say there's a deadlock. Just say there's a deadlock and you're fine. Don't have to worry about it. All right, so we want another question. So this was a threads question. We did that. Someone wanted what? A thread and semaphore problem. Okay, we did that one. No, that's all we got. I think we're out of ones I have on hand, unless there's a semaphore question here. Oh, yeah, there is, because we just did the first parts. All right, so we can do this semaphore question. All right, assume your semaphore works. Good assumption, huh? Assuming a functional semaphore implementation, so just assume it's our normal semaphores. Analyze the given code where init initializes the semaphore sema before we create two threads. One thread executes T1, the other executes T2. So we have thread 1 that's set up to start executing this thread. Thread 2 that's set up to executing this thread. Our goal is consistently print tic-tac-toe in that order. Analyze if this implementation can lead to a deadlock. Explain your reasoning. And a deadlock could be just any thread waiting. So, can this lead to a deadlock? Well, let's see. So, if the initial value of the semaphore is 0, so we don't know which thread. So, if T2 goes first, it hits wait, and it can't make any progress because the current value of the semaphore is 0, so it can't do anything. So, only thing that could happen is T1 prints tick, so it would print tick, and then has no other choice but to post. So it would post, then that initial value of that semaphore is now 1. Now, no matter, I don't know which thread can run next. Let's assume that it is T1. So if T1 executes next, so what I'm looking at right now, leading to a deadlock is, okay, well, posting a semaphore allows something else to run, right? It increments the value. So I'm trying to look at the path that doesn't post and kind of prioritize going to that. So at this point, this is where my fork in the road happens, right? Because I could execute T1 or T2 at this point because the value of the semaphore is 1. So here, I'll assume T1 executes. So it would atomically decrement that value from a 0 to a, or 1 to a 0. And then it would print toe, whoops. Then it would print toe. And then exit with that value, and then it's done. Then thread 2, oh no, the value of the semaphore is 0. I can't make any progress, so I would say yes, T2 can get deadlocked. And basically just explain what was going on there. And it says, modify the semaphore-based code to reliably print tic-tac-toe in sequence. You may use additional semaphores if necessary, you may directly annotate the code listing to refer to the numbers in your explanation. So for this, for semaphores, easy way to think about it is, well, I probably need a semaphore for each condition. So there's one condition here where that tack should print after tick, and another one that toe should print after tack. So I have two conditions. I need two semaphores. So I can call this one sema1, and well, for the first condition, that is going to be waiting on the tick to complete because I don't want tack to happen. So this would be a wait for sema1, and after T1 prints tick, then it would post sema1 so that the other thread can actually make progress and print tack. Then I could create another semaphore called sema2 because I am creative. Then place the wait first, so I want to wait to print toe until after the other thread has printed tack. So thankfully this wait's already here. I just change it from sema to sema2, and then initial value should be 0, so I don't want to make any progress until the other thread is done with tack. And then here I would just post after tack and be done with it. So I'm good. Then I always print tic-tac-toe. All right. So that was a summer question. That was that. That was that. Yeah, so for this question, only thread 2 gets stuck. You can consider that deadlocked. At least one thing gets deadlocked. So just say that one thing that gets deadlocked. How important is it to know the varying file allocation strategies like fat, linked, etc.? Linked, I mean, just know them high level, right? Linked is a linked list where there's next pointers on blocks. It's kind of slow. File allocation table just moves the next pointer to a separate block. Still that same idea. Files described by a linked list, contiguous, basically like an array. And then for indexed, well, I'll use an array for each file instead of trying to treat it, each thing as like an array of blocks. For this deadlock question, is it also valid to say lost wake up issue between post and wait will cause a deadlock? So technically not a lost wake up, because a lost wake up usually means you explicitly put the thread to sleep and then you wake it back up, either doing thread sleep and thread wake up, or a condition variable wait and a signal, because basically it'll just do a wake up. Next one, for question 40, the RMB just delete the hard link entirely. Why does it not disappear even though the hard link, yeah, it would delete the hard link. We did that file system question in one of the lectures. Yeah, so we did this file system question in one of the lectures because it has green check marks. So check, I forget what section it was. I think it may have been section 2's review, so check that. Semaphore question, wouldn't T2 be lost wake up instead of a deadlock? So technically not a lost wake up because like it's properly asleep. No one's signaling it to wake it up. And the other thread did what it was supposed to do. It passed by wait. It just got stuck in a wait. So just the generic term stuck, just say it got deadlocked. So sleep, lost wake up is generally some thread is asleep and it should have been woken up by another thread. All right, any other things we need to go over? We still got a bit of time left. Everyone excited for their final exam on a Saturday with the TTC line down as well? Yeah, P.S. if you didn't know, line 1 is not, well, they're operating buses, I guess, but the subway is not running on tomorrow, which is fantastic, huh? In the threads question, why is there a data race if the join is fails? All right, so this was the question that I regretted. So we have this. So, given what I wrote, it is possible that, so let's just have it as written. So, for this question, what's possible to happen is, so let's say I have, I'll use blue. So let's say I have my initial main thread. So my main thread executes, changes that global variable from a 0 to a 1, no problem. Then I create thread 1 or thread 0. And then before creating thread 1, well, thread 0 executes, creates a local variable called y, no problem. Joins on some thread that doesn't exist yet, so it will pass by this, no problem, and just get an error. Whoops. And now I don't know what's going to run. So main could run next, create thread 1, then thread 1 is here. Now thread 0, it's set up that the next thing it's going to do is modify the global variable x. So x plus equals y is just reading x, adding a local variable to it, and then writing it back out again, which is just like plus plus x with an extra step. And then thread 2, the next thing it's going to do is update y. So this will do another read and write. So this is basically like two threads about to call plus plus, like count plus plus. So there's a data race between them. They could both read the value, the current value of x, which is 1. Right, so thread 0, thread 1, they could both read the value of 1. And then at this point, either one could execute, we don't know, but they both read that initial value of 1. T0 would internally in its local variable increment its value to y is 3, so it increments it to 4, and then updates x to be equal to 4. And then thread 1 goes, and well, it just adds 2 to its local, to get us a value 3. So it's going to update the value of x to 3. And it could be either of these. So the final value of x could be 3 or 4. Well, if it just ran without any data races, right, it would be much larger. It would be 7 or something like that. I forget. So that's bad. So that's, the question was not intended to be that hard because there's a whole lot of other ways they could all go. All right. Sorry, just to confirm, SAR4 is called deadlock. It's once one thread is docked and we don't check the 4 conditions for deadlock. So yes, deadlock can also just mean like no thread can make progress anymore, right? So deadlock, the way we've mostly seen it, and the 4 conditions for deadlocking is like mostly when we talk about that, it's in the context of mutexes, right? Just means you'll call mutex lock and you'll never return from it. You'll never get that lock. Same idea for center 4 is I call wait and I never actually make it past that wait. So just deadlock, not making up. Is it possible to go some short answer, high level conceptual questions, maybe questions on virtual machines containers? We did 2 of them today and did a bunch in the review lectures, so check that. I think we've covered that. If we have a function running a thread and it forks, is that new process a child of the main process that created the thread? So threads are all running within a process. If you call fork, that new process is a child of the current running process. So yes, but that new process that got created is only going to have a single thread in it, and it's going to be a copy of whatever thread called fork, which kind of a bad idea when you have multiple threads. All right, did I clear everything? Just retype anything if I missed anything, but I think we got everything again. Or anything else we need to go over. Apologize if I missed anything. Does RAID 1 have an affinity to a specific drive? So no, RAID 1, every disk is treated exactly the same. They all have all the exact same data on it. Other ones, some disk questions. So disk questions is probably like a short answer, if that. Short answer. Here we go. Comparing two scenarios where you have 4 disks configured in RAID 1 and RAID 5, respectively, if a single disk fails and is replaced, which RAID configuration would recover faster and why? So this one is simple. So say I had 4 disks, so we can use this as a bit of review. So actually, let me redraw that. Woo, that was bad. All right, so if I have RAID and not RAID Shadow Legends. If I had RAID 1, then every single disk is a copy of each other, right? So this disk is a copy of all this one, so they're all identical. So I could just say X, 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 X. They're all the same. If I have RAID 5 with 4 disks, then it's basically a stripe of 3 drives, so I would have like X, Y, Z, all containing different unique data, and then I would have my 4th disk at the end. That would be a parity disk. That would basically just be an XOR of all the other disks, right? So this is our parity. So if I fail, so if I have one disk that fails for either, say it's this one, or even if it's the parity disk. So if I want to recover RAID, if I buy another disk in RAID 0 that has nothing on it, and I want to be a copy of the other ones, right? Well, this is really fast because I could just get like a third of the data from each disk. So I could have, you know, I'll take the top third from this disk, copy it over to this one, take the middle third of this disk, copy it to this one, and take the bottom third of the last disk and copy it to this one. And copying's really fast, don't have to do any calculations or anything like that. In order to reconstruct, you know, the parity disk, I'm going to reconstruct a single row. Well, I have to read from every single disk, right? I have to read everything from Y. I have to read everything like that first, well, the whole disk, but let's say it's just a little bit of it. I have to read it all from all of these disks and then recalculate the parity, which is going to take some time. Also, I have to read the data from all the other disks, not just a third of them. So it's going to take a long time to recover that reason. So basically, the shortest answer is in RAID 1, I just calculate, in RAID 1 to recover, I just copy a third of the data from each disk to the new one. In RAID 5, I have to read the entire contents of all 3 disks and also recalculate the parity. And yeah, so RAID 5, the parity is going to be striped. This is technically RAID 4, but you know, drawing it is a lot harder. So RAID 5 is basically RAID 4, but it's distributed. So just imagine it's distributed too. same idea. I'm going to have to read the contents of all the other disks. If I have RAID 5, I don't have to calculate the same amount of parity if the parity disk died, but same idea as before. So yeah. And no, you don't have to know RAID 2, 3, 4. We didn't even go into RAID 2 and 3. If a RAID 4 parity drives, is it over? No. If the parity drive fails, then that's fine. Then it's just basically a RAID 0 that's still working. You have all your data. But yeah, RAID 5 is technically distributed. It would be slightly more complicated than RAID 4, but you know, I essentially have to recalculate the same amount of parity from all the other disks. So it's a little bit different, right? Because if in RAID 5, if one of these disks dies, then whatever, well, I actually need to read all the other disks, so it doesn't matter. It doesn't matter if we distribute it at all. So yeah. All right. What was the other thing we wanted to go over? Oh yeah, the RAID Shadow Legends comment. Okay, we did that process question. Go over macro kernel, one above it. So the macro kernel, this is made up. This is just some made up term I made because we know there's, right? So there's like a monolith. So there's like a monolithic kernel, right? That has a whole bunch of stuff in it. And then there is a microkernel that has less stuff. And like research-wise, like essentially on the side graph, this is like the size of it, right? So monolithic kernels have way more stuff in them. Microkernels are like, hey, we want to keep more stuff out of kernels. So if I have the microkernel, right, we talked about like nano and pico, try to make that even smaller and push the boundary. This macrokernel made up term where I was like, hey, what about if we took monolithic to the extreme, right? And we just shoved more stuff in there. So I probably should have explained that I just made up the term, and that's what was like, hey, let's throw more stuff in kernel mode. So this basically meant like, let's actually implement our kernel or our web server in kernel mode, which, funny story, that's what happened in one of Microsoft kernels, because the Linux kernel had way better performance for web servers, and they're like, well, how do we get some more performance out of this? And then they actually implemented a web server in their kernel, which was a bad idea. So one advantage was that it was fast. One disadvantage is if there's an exploit in your web server, hey, you now have control over the kernel. Probably very, very bad for security. And yeah, so the reason we use RAID 5 is to distribute the parity, because if we just had a parity disk like in RAID 4, it essentially gets like however many disks there are. If you update any one of them, you always cause a write to the parity disk, so it's going to be unfairly written to and wear out a lot faster because it's going to get a lot more write. Yeah, if someone wrote a kernel in PHP, I mean, they probably had fun, I guess, but no one's actually running that. All right. Yeah. Is PHP compilable to assembly? Everything can go to assembly eventually. You can compile the interpreter and do whatever. You can eventually do it. It's just whatever the default is. No one should use PHP though. Yeah, I think the guy who started PHP, I think, went to Waterloo. So yeah, good history there. All right, and anything else? So yeah, advice, if you practice the other finals and kind of high level thought about it, you should be mostly okay. Your final, I would say some questions are a little bit harder than the past ones, and because of that, I've made some questions easier. So I think it should even out. All right, anything left in our 10 minutes? I'll also post on Discord if I happen to make it to campus early. Going to Toronto on the weekend, I'm not super looking forward to my commute, so don't know how long that will take. But I'll let you know whenever I'm in my answer. Length of it compared to the previous file should be pretty much exactly the same. I tried to, so was it, which file did I screw up on? Yeah, so this file didn't have very many short answers. Yours has slightly more short answers, but I think they're shorter, and you have a bit, yeah, like the format's pretty much the same. Still confused. Piping. If a process write to the pipe, the child would immediately read from it. No. I'm not sure why in the given question the child process would read 42 and 332 separately. Why can't one of them read both numbers? So they could, but if you look at the read calls, the buffer size is only 4 bytes. That's why. If it was 8 bytes or something larger than 8 bytes, then one process could read both of them. But specifically in that question, that read call only reads an int at a time, so that's why they both read them separately. But yeah, if it was like just a huge big buffer, then we won't know. It could read both of them at the same time. So you're right. For this question solution, still technically changing, increasing the number of overall pointers. So that was that file system question we went. So that would just be changing the so basically that says add and that, or remove then add. I guess you could just say change instead, but same idea, right? So instead of using a direct block as a direct block, I'll instead repurpose it and use it for a quad block. So it should say change, not remove. So remove and adding is functionally the same as changing something, right? And yes, the parent needs to close the right end there because the other processes just read their byte and then terminate the process, which closes the file descriptors. All right, so everyone is now more ready for the exam tomorrow. Dun, dun, dun. When would we use pthreadcon signal and pthreadcon wait instead of regular lock and unlock? So you'd use condition variables for ordering instead of center fors if what you want to wait on is more complicated than just a number. You wouldn't use it in place of lock and unlock. That's for mutual exclusion, which is for data races, not ordering. Can I quickly go over number 4? What's number 4? Oh, the uContext one. All right. What is the outcome of running the code snippet? So we create a context, get context. Whenever we get context, whenever it will save the current context, and whenever we store it, it's exactly like we just returned from the latest get context function. So we would come back here, come here, whenever we set context. So after that, let's say this red arrow is what we're currently executing. It would call set context, which would immediately put it back to get context. So then call set context, immediately restore it here. Set context, restore here, set context, restore here, and do this over and over and over and over and over again. So it'll infinite loop. When will we use pthread read and write? What's pthread read and write? Like a read-write lock? So you typically use a read-write lock to protect a data race, but you also, like, if we use a regular mutex, even if we're just reading, only one thread can read at a time if we're just using a plain old mutex, right? But we know as long as there's nothing else trying to write at the same time, we could have multiple readers. So a mutex by itself doesn't convey that meaning, doesn't let you do that, right? It just one at a time, that's all it cares about. Read-write lock will only have one writer or multiple readers, which is still preventing that data race, but you would do that if in your program you want to actually have multiple readers going in parallel because you know that's safe and you want to do it for performance reasons. So yeah, the one with ++x, it didn't help at all because, well, both of those were just protecting, like, they're protecting a memory read and a memory write, which are which we assume are atomic anyways, so it didn't do anything. Yeah, when you don't try to change the value at all, where you're just reading it, but you want to make sure that you're not reading it while another thread is writing it. So then you just do a read lock. Multiple threads can all have that read lock at the same time. All right, anything else? Anything actual last minute? Again, I'll post on Discord if I happen to make it on campus early. Again, driving into Toronto, not great. Or if anyone wants to help me move a desk, that would, or move a table. So question, why would set context move to the previous line of code and not to the get line? So set context is basically like a restore, right? It's going to restore the values of the registers to whatever you last saved them as. And the only function that saves them is get context. So when I did the get context, I saved the registers in the state where if I restore them, the program counter and all the other registers get restored such that it looks like I'm returning from that get context again. So calling set context, that restores, it would restore back to here. Set context restores back to here, restores back to here, restores back to here. So wouldn't move to the next line because that's where I called get context. All right, so with that, I will keep you updated. Good luck on the exam. Hopefully it will not be too bad. Again, I completely forget it because I wrote it like 2 weeks ago. So I forget what's on it. So you'll be just as surprised as I am. So good luck. I will see you tomorrow. And yeah, I guess good luck. Bye.